Happy morning, Darshana.
Hello, Professor. Good evening.
Yeah, happy morning for you.
I cannot hear you though. Am I audible?
Yeah, you are audible. Maybe like I'm
It's still same.
driving. Just I'll
Maybe
stop
are you
there and.
driving or it looks
Yes,
like you are
yes,
in the
yes, yes.
car, but I cannot hear
Yeah.
you still the same.
Give me a couple of
Let
minutes.
me check
I'll.
my.
Yeah, give me a couple of minutes. I'm going to like stop and join. No issues.
Can anybody from participant try just on your audio and say something just to make sure that I am audible to everybody, and also I cannot hear Professor.
You are audible, Darshana.
Let me check.
Hello.
हाँ आई जाओ प्रतीक मैं ऑफ कर Hello, Professor. Can you say something? Just want to make sure you are audible.
Happy morning. Happy morning. Are you able to hear my voice? I'll rejoin. Give me a sec.
Hello. Let me connect again.
Hello. ಇಲ್ಲ ನಾವು
Hello. Am I audible now? I still cannot hear you. I don't know what's going on. Yes, now I think I can hear you. Background voice. Can you say something, Professor?
Hello. Happy
Yes.
morning, Darshana. Are you able to hear my voice?
Yes, perfect. Now I can hear you. Sorry, something I think wrong at my side probably.
I think have you muted? I'm not able to hear your voice.
Oh,
Let
you
me
cannot
check.
hear me? Oh, that's weird. I can hear you. Let me check.
Sir, we can able to hear, sir.
Hi, am I audible?
Yeah, you are
Yes, ma'am,
audible.
audible, ma'am.
Perfect. Thank you so much for the confirmation.
Yeah.
Finally. I don't know. With remote access, it's always like that.
Yes.
Last minute glitch. How are you
Yes.
all? Hello,
Yeah.
Professor. So
Yeah.
good to
Doing
see
good.
you after a long time.
Yes. After a long time.
That's
How is the
correct.
winter going on?
Oh, it's crazy here. It's lot of snow this time. It's like a
Yeah,
snow mountain outside.
I come to know from professor too. Usually kids only they will enjoy, but we people like struggle a lot.
Agree.
Yes. So normally people will join in another 5 minutes, and we used to like start by 6:35. So for your time, 85,
Perfect.
8:05. Yeah.
Sounds good.
Yes. So Sister is working on cryptography like a simulator, right?
That's
Is it
correct.
right?
I'm planning to show you something today. So I'm
Okay.
planning to actually focus on one of the projects that we have been doing. It's
Okay.
kind of a hybrid cryptography which combines post-quantum, quantum, and classical cryptography. And then I'll show you one of the post-quantum cryptography simulator that we have designed to
Okay.
compare and evaluate various CAMS algorithms. So that's the
Yes.
plan for today.
Yeah. So today the people are going to like enjoy as you are going to like show the real time, right?
Yeah, I'll try my best, though it looks like still it's more theoretical because a lot
Yeah.
of
Yeah.
presentation.
Yeah. Yeah.
But
I understand.
I'll
Yeah.
show you the
Cryp-
simulator.
Cryptography is like a cryptography. So little
Right.
bit like if we take it like a very interesting, it's interesting, and we will
That's
enjoy. Otherwise,
yeah.
it will bore.
I'll try to exclude mathematical things, more
Yes.
over realistic approaches, but though
When I
it's
was
more
a student, I do remember because for security and other purpose also, Professor Lang asked me to like do the stochastic process course.
that's correct.
Yeah, I do remember the days.
Yeah,
Yeah.
agree.
Oh, okay. Shall we start? I think usually by the time more than 50 plus participants used to come, but I don't know why today. Maybe like because of Saturday. I don't know.
I those so like 27, 28, 29 participants though. So it's
29 plus 7. Yeah, 35 participants.
oh perfect.
Yeah, usually the G meet full because
Mhm.
total number of participants registered is 175. So we
Right.
posted, yeah, we released our poster just 3 days before only. So we submitted our proposal last. It took a long time for getting approval in my management. Yeah,
Agree.
yeah.
So today is the last day of your
No,
workshop.
no. The thing is, my part have to yet to complete. So that I need to because right. If I discuss something on cryptography and related, because I try to like discuss. It's a kind of like a for my personal things also. I want to build a group for like a research group on quantum. So for that, I'm planning to like reading all the papers. So in all aspects from like a quantum switches gates and simulators, and then optimization algorithm, qml, and cryptography. In all the aspects I'm touching. So what is the current research and what is the future direction? So that's what it taking bit time also for me, so that
Right.
yeah, once you complete it, then only if I give the that part, I think it would be fine. That's what yesterday I didn't give. So
Right.
Monday I'm completing this FDP.
Perfect. Yeah, that makes
Yes.
sense. If they have a
Yeah.
basic like knowledge of PQC, and then if you can shift to quantum, that becomes
Exactly. Exactly.
especially cryptography.
Ma-
I think we need to mute. I
Ma'am,
don't.
Janila. Yes. The kids are
That's
talking. Yeah. Okay, I think better we will start. I'm inviting you since this is the official. I would like to invite you in like a official way. So very good evening and good morning, happy morning for you, one and all gathered here. through online meet. So it's a great privilege and honor for me to like welcome you, and you are the esteemed resource person for us. This is day 5 session of the faculty development program on emerging trends in quantum technology. So it's we are delighted to like host Dr. Darshana Upadhyay as accomplished researcher and academician and technology like an expert in the field of IoT, quantum, embedded systems, and all those things. And Madam currently serves as a research scientist at Tele Corporation, and is also a adjunct professor in Dalhousie University, and she has made the remarkable contributions in the area of algorithm conceptualizations and hardware design and all those things. So with extensive experience in academia and industry, and she also worked on like a cutting edge research like on integrating machine learning and deep learning, blockchain, and all those things. So she played like a significant role in mentoring researchers also, because I do remember the days even my UG research scholars also got benefited. So we are indeed fortunate to have such a eminent, distinguished expert among us today. So to share her knowledge and insights on both theoretical as well as the real-time whatever have done on their part. So I'm very confident that today's session will greatly like enrich, and the participants will really enjoy the session today. So I wish this session would be like a fruitful and happy session. And I invite Dr. Darshana Upadhyay to take over the session, please.
Thank you so much. Let me share my screen.
Yeah.
All right. So are you able to see my screen? If anybody can just let me know.
Yes, it's visible.
Oh, perfect. Thank you. All right. Very good. Okay, so thank you so much, Professor, for a great introduction. Hello, everyone. Just again, I just wanted to quickly introduce myself. I'm Darshana Upadhyay. I'm working as a research scientist at Tele Corporation. And today I will briefly walk you through our research focused on quantum resistance hybrid cryptography. So before I formally start, I want to focus on why our research is important and necessary to explore. And this is one of the projects that we have been doing in our company currently. And I would like to focus on some of the focal points before I'll dive deeper into the methodological aspects. So currently, research community along with us are anticipating two major technology shifts. One is LLM, generative AI, and we all are witnessing its impact now, right? Like without ChatGPT, even we cannot think our starting of the day. And the second is quantum computing. It is still an emerging technology, but we never know when it might become a mainstream, just like the generative AI did, right? Even we didn't think about generative AI before, and suddenly it came. Similarly, for quantum computer, still it is emerging, but we never know when it will be really adapted, and it will completely, once it will be adapted, it will be completely shift the paradigm. So it, and once it comes, it is having a high computational speed, and because of that there could be an impact on existing security applications, because almost all of the existing security applications are rely on classical algorithm. Now the problem with the classical algorithm is when it emerged, it did not think about the quantum computers, and that's why once the quantum computer has its own exist, then because of its power, it is having an ability to break the classical security easily. And that being said, we can't afford to wait until quantum computers are widely in use. We have to be a little proactive and start exploring the solutions that can protect the existing application from the quantum attacks. So that's the major aspect of this particular application that we have been working on. Also, we need to kind of consider the classical algorithm. We cannot fully remove the classical algorithms, right? Because that's the classical setup we have been following on. So we have to make sure that our solution that we try to incorporate, that should persist the classical algorithms as is. But on top of that, we need to create kind of a defense on depth architecture that will integrate post-quantum and quantum cryptography in a real-time communication application. So what we have been doing for this particular work, we have been exploring the integration of classical, post-quantum and quantum cryptographic techniques to develop a secure solution for real-time communication application. So let me now quickly, first of all, briefly dive deeper into the difference between classical, post-quantum and quantum cryptography. So here you can see that classical algorithms, as we all know, it depends on the mathematical algorithms. However, if we consider the security aspects, it is vulnerable to quantum attacks. Though we know that it runs on the classical computer, so we don't really require something very special. The algorithms, well-known algorithms that we know is RSA, EES, and ECC, which are widely used currently in, I think, in every application. Now the another cryptographic solution is post-quantum, and we might think that why we require post-quantum. So as I already mentioned, that if quantum computer has the power to break the classical algorithms, because it's fully rely on mathematical algorithms. However, when they start looking into post-quantum algorithms, now they consider the quantum computers, and hence the foundation of these algorithms are kind of NP hard problems that is very difficult for quantum computers to break. So post-quantum cryptography has an ability that it will resist to classical attacks as well as quantum attacks. So it is a kind of a solution that you can use to your classical computers as well. So this is having a capability of resistance to quantum attacks. It runs on a classical computer, so you really don't require any special hardware. And there are different types of algorithms like lattice-based, code-based. So I'm going to talk on these algorithms later in the slides. And it is still being standardized. So we will also see the standardization process, that which are the algorithms which needs to consider to be a top algorithms. And the third category is the quantum cryptography. Now, quantum cryptography requires a specific specialized quantum hardware. So it's not a kind of a device that we are going to use, but it is having a specific quantum hardware, and it is using the quantum mechanic principle, which is a kind of a physics. It's rely on the physics principles. And definitely it is provably secure using the quantum properties, and it requires, as I mentioned, specific quantum devices and infrastructure. And there are very well-known algorithms like some of QKD algorithms and also QRNG, which is used to generate the random number, right? So I guess in today's methodology also, I'm going to use QRNG, a concept of QRNG from quantum cryptography. I'm going to use PQC for key exchange mechanism, and I wanted to combine these two algorithms or two methodology with classical algorithm to make it hybrid but quantum resistance. That's the plan, but we will see it later step by step. So before we will dive into the methodology, I would first of all go for some of the basic idea about the post-quantum cryptography. So here you can see that, let me have my laser pointer on. Okay, So here you can see that, as I already mentioned, that post-quantum cryptography is used to design to resist the quantum attacks. And why it is necessary? Because we cannot now rely on the classical algorithms because of the quantum computers. That's why it is now necessary to migrate the solution of post-quantum cryptography along with classical cryptography. And that's how the NIST, which is National Institute of Standard and Technology, this institute has launched a standardization effort in 2016. So what this NIST has done is, it officially launched a global call for post-quantum cryptographic algorithms. And during this call, they invited the researchers worldwide to submit the candidate algorithms that could resist the quantum attacks. And this particular consortium, they have focused on two types of submission. One is key encapsulation mechanisms for encryption and key exchange. That means you want to, sorry, I think something is going wrong. All right. So, what happened in key encapsulation mechanism? That it first of all securely exchange your seed, and then using that seed, they started doing encryption. So it's kind of an encryption algorithm, but it will first also try to exchange the seed securely. That's called key encapsulation mechanism. And second is the digital signature scheme. This is specifically more about the authentication part. Now, what happened in 2016? They started. They actually launched the call for algorithms, and then during 2017 to 2022, they had a kind of a 3 rounds, and during those 3 rounds, they got around 82 submissions. And like from those 82 submissions, they got the 4 finalists. So if you see here in 2022, they have the finalist Kyber, which is a CAM algorithm. Dilithium is again a digital signature, Falcon, and Sphinx is again a digital signature scheme. And in 2024, they officially make this standard as a federal standards under FIPS 203, 204, and 205. And again in 2025, they wanted to have one more for the algorithm diversity. They wanted to have one more algorithm included. And during round number 4, they have added HQC as an additional CAM. So if I just wanted to quickly show you the category of these algorithms. So there are 5 types of PQC algorithms, which is lattice-based, code-based, hash-based, multivariate quadratic equation, and isogeny-based. So we are not going to go too much of detail into the mathematical terms, but just wanted to give you a quick overview of some of like the categories of these algorithms under which particular type. So lattice based, generally it's a hard problems based on ring LW and SVP. And then the advantage of these algorithms are they are very efficient. They have a small keys and strong reductions. The disadvantage, if I will consider compared to classical algorithms, especially the RSA and ECC, then this is kind of a complex algorithm in terms of implementation to understand. But definitely it's a NP hard problem, so that is the main concept behind it. And if I will consider the examples of lattice based algorithm, then those PQC algorithms are Kyber, Dilithium, Falcon, and NTRU. So in my research, I use NTRU and Kyber. Dilithium is a kind of a signature based algorithm, but Kyber and NTRU is, I guess NTRU is also digital signature based, but sometimes we can also use NTRU encrypt for the encryption as well. So NTRU has 2 variants, one for encryption, one for digital signature. Kyber is for encryption, which is key encapsulation mechanism. Now code base, it based on the error correcting codes. And again, the advantages of the code based PQCs are it is having a long history, high security, resistance to the quantum attacks, but it is quite costlier than lattice based algorithms. The disadvantage is it's very large public, so it's generating a very large public key, and if you are really thinking about the highly available system, then probably this will be not a suitable candidate. And the examples are HQC byte. So these are the HQC is the finalist, though fifth finalist of the competition. Bike is a bike. I also see like a lot of researchers have started looking into bike as well, and they are trying to modify this algorithm as well to make it more stronger. Hash based algorithm, those builds on hash functions, and the advantages is it's proven to security. There is no algebraic assumptions for this. The disadvantage is again it's a large signature, slower signing. Well-known algorithm I would say for which researchers are using is swing. So swing is one of the candidate if you are planning to incorporate the hash-based algorithm. Another is XMSS. This is again another good candidate to consider. Then the another type of algorithm, type of PQC algorithm is multivariant quadratic equation, which is based on the quadratic equation. So the name only suggests what it does. And the advantage is it's a fast signature and short signature potential. So it's generally it is used in digital digital signatures. The disadvantage is again it's a large keys history of broken schemes, so that means it's still not worth considering it because of it could be vulnerable to attacks. And the examples are rainbow and UV. And the fifth category is isogeny based. So it uses the kind of elliptic curve theory, and then the advantage is it's very small keys. So if you have a short communication or if you want to send some short messages, then probably this is a good candidate. But if you are thinking of large messages, then probably this won't work in that case. So one of the application I would consider is industrial control system application, where if you want to on or off the motor, or if you want to just turn on the valve of the pump, you just wanted to send a very short signal, right, on off kind of thing. So that time probably you can use isogeny based PQC algorithms. So here is the comparative analysis. I'm not going to go into the detail, but you can see that these are the 5 finalists: Kyber, Dilithium, Sphinx, Falcon, and HQC. And you see the categories, you see the security basis, what key size they considered, the signature, performance of each algorithm, what are the pros and cons, and definitely this is the standardization status for now. So if you see that it is finalized in FIPS and considered in FIPS as well. Now, this is the just a short summary that I already mentioned before, so I'm not going to go into the detail, but at least you should know that Kyber is used for CAM, Dilithium and Sphinx, those are used for digital signature. And these are 2 backup CAMS candidates. Those are Falcon and HQC. So 3 CAMS candidate, Kyber, Falcon, and HQC, and Dilithium and Sphinx are used for digital signature. All right. Now let's focus on what are the challenges with classical cryptography and the path to quantum resistant security. So we need to first of all understand that while classical algorithms like RSA and AES has protected us for decades, right? They were never designed to handle attacks from the quantum computers, as I mentioned earlier. But once the quantum computers arises, it could be possible that because of its high computation, it breaks the classical cryptography. Hence, it is very important that we need to have some defense in depth architecture that will retain the classical algorithms as is, but on top of that, if we can integrate post-quantum cryptographic solution, then it could defend against the quantum attacks. So what we have done is, in our methodology, we have provided a kind of a hybrid approach. This hybrid approach will consider the post quantum solution as well as we consider the quantum solution. So I'll go through the methodology later on, but I just wanted to tell you what is our aim. So our aim is to enhance the security of communication system in the post-quantum era, leveraging a hybrid cryptographic approaches by integrating post-quantum, classical, and quantum cryptographic methods. So before we'll dive into the methodology, let's quickly go over the research gaps. What are the research gaps that we have focused on and how we have incorporated to address these research gaps? So one thing that we observe is there is a lack of comprehensive comparative analysis of various PQC-based key encapsulation mechanisms, which focuses on performance, security, and real-world implementation. So what we have done, that we have created a kind of a simulator. I'm going to show you that simulator, that using that simulator, you can compare the various CAMS algorithm in terms of the message size, in terms of the randomness, in terms of the security. So, and then we have identified which one is best. Though the NIST already suggested, right, the Kyber is the best algorithm compared to the other algorithms. But we decided to do the comparative analysis in terms of these three factors: performance, security, and how it is really suitable for our own application, because we are working on real-time communication application where highly available system is our main aspect. So we need to make sure that the way we are generating a key, the way we are exchanging the key, and the way we are using the encryption algorithm, it won't be so costly that it will not provide the high availability. So that's the one factor we need to consider. The second research gap that we have identified is current studies do not adequately evaluate the PQC systems in lightweight or resource constrained communication scenarios. As I already mentioned this, we need highly available system. That's why we need to focus on how adequately we can consider PQC in our methodology. The third point is insufficient exploration of combined effectiveness of PQC, QRNG, and classical techniques. So generally what we see is whether the solution is purely classical based, or the solution is purely PQC based, or the solution is maybe quantum based, right? But our target is different. What we want is, we want that we cannot delete classical totally, because that's the algorithm which everybody is using. So we should use the classical, but on top of that, how we can integrate PQC and quantum, that the quantum computers don't have ability to break the algorithm. That is what our final goal is. And then to make it, because finally the strength of the algorithm is always based on how strong your key is. So while we are generating our key, we have to make sure that the key should be unpredictable, and it shouldn't be guessed by any intruder. So for that purpose, we use the whitening technique and cryptographic hash function. Now, as I already mentioned, in our solution, we use the cryptographic hash function Sphinx, which is again based on PQC. So ultimately, we are considering the PQC hash function. We are considering the PQC CAMS architecture as well to register against the quantum attacks. Now, here is the novelty and objective of our methodology. We have conducted the comprehensive comparative analysis of post-quantum cryptography based CAMs, focusing on performance, security, and implementation. So this is the first step we have done. After that, we have proposed and implement a hybrid cryptographic protocol, and we gave the name of that protocol is called Secured Message Protocol with Dynamic Secret Key, combining PQC, quantum random number generator, and classical techniques. The third point, what we have done is we have enhanced the key randomness and security using the whitening technique and cryptographic hash function called key generation cascade. So the cryptographic hash function that we have used is Blake 2s, but this is a kind of a classical algorithm, right? So even we can replace, that's what we have done it now as a next study. We replace the Blake 2s with the Sphinx, because Sphinx is a kind of a PQC algorithm, and that's what I feel like it's more suitable compared to consider the Blake 2s, though it is not yet identified that it is breakable by quantum computers, but we never know. It's ultimately a classical algorithm, right? So if we consider PQC, then I guess Sphinx could be a better fit candidate. And then we have evaluated the proposed system in terms of efficiency, randomness, and resistance to the quantum attacks. So let me now talk about the proposed methodology, where, as I mentioned, we have used a hybrid approach using modified Kyber, QRNG, and KGC for Vernam cipher. So before I dive into the methodology, I just wanted to tell you in a very brief nutshell that what we have done is we use a Kyber. Now, Kyber is a post-quantum cryptography. So while we are exchanging the key, we use Kyber, but we don't use the Kyber as is. We have modified the Kyber using QRNG. So we have integrated the quantum part to the post-quantum cryptography. And once we modified the Kyber, we have exchanged the keys, and then we use the Vernam cipher. Now, Vernam cipher is kind of a classical algorithm, right? But it is a very straightforward algorithm. You need to just use the modulo 2 operator. It's just an XOR. So you're XORing your message with ciphertext with key, and you will get your ciphertext. Now, the security strength of the Vernam cipher is that your key should be always unique. That is the important aspect of the Vernam cipher. So once you use that key, you throw that key. If you use that key again, that means it is vulnerable to attack. So how you can generate these keys always unique? So to generate the key always unique, we use QRNG, that is quantum random number generator. And as we all know, the difference between PRNG and QRNG is that PRNG is pseudo random number generator. That means there could be a possibility that after a certain instance, again it will generate the same key, or there is a mathematical equation where you can at least identify the certainty of the keys, right? So it's not truly random, but using QRNG, you will always generate the true random number. So true random number generator, you can design using QRNG. So we have used QRNG to generate our key. So just to give you an overview, we have used a hybrid approach that combines PQC-CAM for key encapsulation along with QRNG from quantum cryptography and KGC for classical cryptography for secure communication. The key components that we need to consider is we have modified the Kyber by integrating QRN as a seed to enhance the shared secret generation. We have used quantum random number generator for dynamic and unique symmetric key, and we use the Vernam cipher with hash chaining using KGC. So for this hash chaining, you probably use Sphinx 256. Now, what are the steps you need to consider? First of all, you need to generate and share the secret using the modified Kyber. And then the step number 2 is you have to enhance the key randomness through hash chaining. So here we use Blake 2, but you can also use the swing 256. That's what we have done as next step of our research, and the paper is under pipeline currently. And the third step is we have followed the dynamic key generation during secure message exchange using 1M cipher. So I would like to quickly show you. So these are the advantage again very quickly. Why we use this hybrid methodology, because it combines the strength of PQC, QC, and classical method. It is resistance to the quantum threats as we use the Kyber and QRNG. It is highly random because we use QRNG and whitening process. So whitening is a kind of when you use the hash function on top of something. So I'll show you what is the whitening exactly. And for whitening, we use this KGC algorithm. That's what I mentioned before. So let me now focus on our proposed protocol SMPDSK. Let's have very simple scenario while we are going to establish a secure communication between user A and user B. I would like to just quickly show you how we are communicating the shared secret. So first of all, user A generates a private public key pair, and user B also generates its own private public key pair, right? This is a very simple scenario when you want to use the asymmetric key cryptography. Now, once you generate the private public key pair at user A, now here is the role of the Kyber. What Kyber does is it generates the shared secret, and using this shared secret, it's convert the cipher. It's also generate kind of a cipher text, and it encapsulate the entire package using the public key of user B. So that means user B can only decrypt it using its own private key. Now, what we have modified here, this is a key exchange mechanism of Kyber. But instead of using PRNG, we have used the QRNG API. We take the QRNG as a seed, and while we are generating this shared secret, we provided the seed from the QRNG API instead of using a PRNG, which is generally provided by the operating system, right? It's a default operating system random number. So this is the modification we have done. Once we generate this, we send the ciphertext to the user B. Now what user B will do, user B will decapsulate it using its own private key. So it will decapsulate it using its own private key, and it will generate the same shared secret which user A has. So this is a step of the Kyber. So this is kind of a key encapsulation mechanism where you are sending your key from one user to the another user, and you are generating or you are exchanging a same shared secret between two communication parties. So now user A and user B both are having the same shared secret key. Once that is done, what the next step is, we did not start the encryption yet. We have generated the QRN using API. So we generated another QRN, which is a quantum random number. We XOR with the shared secret because user A and user B both has the shared secret, right? Why we need this? Because we want that the user B should also have this same QRN, because I wanted to introduce the whitening process. And for whitening process, it is important to have at least 2 or 3 random values to make it more randomized. Actually, we used it. So now if you see here, the QRN XOR with shared secret, we generated the ciphertext and we send it to the user B. And what user B will do, because user B already have the shared secret, so what it will do, ciphertext XOR with shared secret, you will definitely get the QRN. So now both user A and user B has 2 seed values. One is QRN and second is your seed value, right? SSH, which is your shared secret. Now, the next step is called the hash chaining. So what we are doing here, we are still not, so this is again still key exchange mechanism, but this is under whitening process. So if you see here, what we have done is we have applied the hash on QRN and we have generated the QRN1. Similarly, we have applied the hash on SS, which is a shared secret. We generated the SSS1. And then using QRN1 and SSS1, we generated the symmetric key. Now, the symmetric key is used for message exchange. However, if we consider the Varnam cipher, then we need this symmetric key always unique, right? So I'll go over that step in a next round. So what we will do now, once we generate this secret key, we will send this secret, we will XOR our message that we want to send with secret key. So, or I cannot say this is a secret key, but it's a kind of a symmetric key because we are now using a kind of a symmetric algorithm for the faster execution, because that's again another objective that we need to fulfill, right? So once we XOR with our message with symmetric key, we generate the ciphertext, we will send the ciphertext over here, then user B will also able to generate QRN1, then it will generate SSS1, then it will generate the symmetric key, and using that symmetric key, it will generate the message again. So if you see these steps, generating of QRN1, generating of SSS1, and then generate the SK, it's called the whitening process. So we are trying to make our key little stronger by incorporating the QRNG every time. So now next time what happened, when user B wants to communicate with user A or user A wants to communicate with user B, it will now use the next SK. Now, if you see that this SSS1, it will consider here and it will apply the hash and consider and generate SSS2. Similarly, QRN1 will be the input of the hash function and it will generate QRN2. So that's why it is called the hash chaining. So you are now you are using these two inputs as your next input to generate the symmetric key. So every time whenever you generate the symmetric key, your symmetric key will be generated using hash function, but this hash function again uses the swing, which is a PQC algorithm, so it is difficult for quantum computers to break. And secondly, even whatever the inputs we are providing, these inputs are generated using quantum random number generator. So it is generated using quantum computer, right? So that means it is difficult for quantum computer to even predict these seed values or to even break this algorithm. So that's the beauty of our algorithm. Now, let me quickly go over the primary analysis that we made for this particular methodology. So first, what we have done is we did a comparison of post-quantum key encapsulation mechanism. So as I mentioned, we try to consider all the PQ chems. So you can get these chems in liboqs library. So liboqs library you can use and compare these 10 PQC algorithms. So we did a comparison based on its type, and then especially this is a kind of a theoretical comparison, right? But in terms of execution speed, what we did is we identify the key generation time of each algorithm, encapsulation time, decapsulation time, then total time, which is key generation plus encapsulation plus decapsulation. And then we also did the NIST randomness test. So if you see here, this is a key generation time, and if you see the comparison, Kyber seems to be most promising in compared to other algorithms because it is taking very less time, and that's why it is effective for real-time application, because that's the critical aspect we need to consider. Similarly, if you see the encapsulation time, Kyber again outperformed compared to the other chems. Decapsulation time, again in terms of decapsulation time, Kyber maintained its advantage, demonstrating faster key recovery compared to other algorithms. Cycle time, which is definitely Kyber will lead it because it's kind of a overall time. So it's key encapsulation, key generation plus decapsulation. And this is the NIST randomness test. So if you are not aware of this tool, it's a very good tool. What you need to do is you need to just generate your binary files. So binary numbers. So like if you, what you can do is, suppose if I want to use the Kyber 512. So using Kyber 512, you generate a binary string. So suppose each string consists of 256 bits. And then you generate at least 100K binary strings. You store that binary file, and then there is a tool called niche statistical randomness tool. So you probably, or I'll send you a link later on. You just download that tool, and then you just upload your binary file to that tool, and then that tool will automatically identify how random your algorithm is. So this randomness evaluation has done using different statistical tests such as frequency test, frequency block test. So ultimately it is providing you the p-value. So if your p-value is less than 0.01, then that test pass. Otherwise you can say that test is failed. So based on your input file, it will check all the tests and give you the output. So this is a one good tool that you can use for the randomness evaluation, and especially it is very important when you are working on your strength of the keys. Now here are some of the findings that we identified. One is Kyber, which provides the lowest key generation and encapsulation time. Another we found is the Sabre, which provides the balanced performance with low encapsulation time. So I would suggest when you can use this, especially when you have IoT device, right? And your IoT device is only sending data to your central server, but not receiving anything, right? Because IoT device generally send its status to the node, to the central node. So that time probably because of low encapsulation time, you can consider the Sabre, because if the IoT device doesn't require decapsulation in that case. NTRU, which is faster key generation compared to older CAMs like Psych, but not compared to Kyber or Sabre. So these are the three candidates that we identified, but after comparing everything, we thought Kyber is the best for real-time communication applications. Now, again, all these three candidates are lattice-based algorithms. So another thing to mention here, that lattice-based algorithms are provided. It's meant, so that's what, like, even researchers have been saying, that compared to code-based and other types, lattice-based seems more more effective in terms of execution time and in terms of resistance to the quantum attacks, because some of the algorithms, even they did not chosen to be a finalist of NIST, right? Now, NIST standardization, as we all know, that NTRU are in the race of finalized, but it doesn't consider to be a top 5. So Kyber seems to be the best performer in terms of NIST standardization process as well. And as I already mentioned, that our main target is sustainability for real-time application. So definitely Kyber is ideal for low latency and high efficiency use cases like secure messaging and IOTA, sometimes in blockchain also, because that's another project that we have been working on. And scalability wise also, the Kyber perform consistently across different security levels and devices, because we tried with various devices. On Raspberry Pi also we tried to run it and see whether we can able to get the kind of the similar results or not. So now let's very quickly go over the performance evaluation of proposed methodology. So we did the performance evaluation of our own methodology, SMP-DSK, with short messages around 100 bytes, and we check. And if you see here, the average key generation time, encapsulation, decapsulation, encryption time, decryption time, then QRN generation and distribution, and average total time, all whatever we got which is in microsecond. That means it is for 100 bytes, at least for the short messages, it is very quick. And we integrated this particular algorithm to our one of the chat application to see how it perform. And it this is the output based on the chat application performance. Similarly, we tried with the long messages, which is around 2 MB of each message, and still we got a very fair comparison, very fair execution time. With we receive our data in a microsecond, so I think we don't have to really wait for too long while we are chatting, right? Because chatting is an application you really require highly available system which respond you very quickly. And this is the NIST evaluation test that we perform to make sure that our key is random in nature. It's very important, especially for our methodology, because we are using kind of a methodology where our entire algorithm depends on how strong our key is. Because we don't use even AES, right? We use Varnam cipher. It's a modulo 2 operator. It's just a XOR. But the entire algorithm depends on how strong our key is. And that's why it is important to check the randomness of the key to see that it is unpredictable in nature. And so here is the conclusion. The conclusion is we have concluded a comprehensive comparative analysis. So I'm going to show you one small demo that we designed a kind of a simulator to compare these algorithms. And we identified that the Kyber outperforms in terms of execution time and randomness. We have modified the Kyber by integrating QRNG as a seed to enhance the shared secret generation. So this is the first modification we have done. Then we have proposed the SMP-DSK protocol, which combines PQC, QRNG, and classical techniques for stronger security. The third point is we have introduced the key generation cascade, which is kind of a hash chaining, right? It's kind of a whitening and hash functions to strengthen the key material. So how do we do that? We did not rely on only one shared secret, but we have relied on two shared secret, which is a quantum random number and shared secret. And on top of that, we have applied the hash and we generated the symmetric key. So the symmetric key that we are generating is using key generation cascade, and it uses the whitening process to make it more unpredictable. In terms of execution time, our method reduces computational overhead, enabling faster key generation and encryption process. And by integrating QRNG and whitening techniques, our method enhances the randomness, ensuring cryptographically secure and unpredictable keys, because that's the final goal of real-time communication. And we validated our protocols suitability for lightweight and real-time secure communication. As I already mentioned you that we use EC chat application, which is kind of a chat application. We deployed the entire methodology and see whether we can able to communicate effectively with a high response time, which is very important. And secondly, we also tried out using a kind of an embedded system environment. So we use Raspberry Pi, which is having a very low resources, and try to execute our code there just to make sure that our methodology is still highly responsive in terms of execution time, memory utilization, and definitely the security strength should be always same whether we are considering it for in any devices. So that's it for the presentation, and let me quickly show you the simulator. Okay. I think let me share my entire screen probably. I mean, this one is better, I guess. Okay, so are you able to see my screen?
Yeah.
Perfect. All right. And uh, so this is the application that we have developed. This is the simulator. It will take little time to load. All right. So are you able to see the simulator window? If
Yes.
anybody can just
Yes.
perfect, good. Okay, very good. So if you see the simulator window, what we have done is you can add even more PQC algorithms as well. We have added for now 6, but definitely using libOQS library, whatever the algorithms I mentioned in my presentation, all the 10 algorithms you can add. And then when you choose a particular algorithm, it will give you the versions of those algorithms variants. So it depends on again the key size. So here you can see for HQC the key size is 128, 192 and 256. Let me take Kyber, and for Kyber you see the key size is 512, 124, 768. So these are the 3 versions we consider. One another thing we consider is, because we wanted to even formulate our own hybrid system, so we consider different classical algorithms as well. So once the key has been exchanged using PQC, then we can use classical algorithm for the encryption. However, whatever methodology I have suggested, that is not implemented yet into this simulator because the paper is under review. So once it is done, then probably we will add here Varnam cipher, but you cannot see the Varnam cipher, but it's just a one step thing. So we have included another algorithms like AES, DES, Blowfish, Chacha20, which again considered to be a very good stream cipher, and Salsa20. And based on these algorithms, you have various variants. We conducted different experiments in a way that if we want to just send a data from one end to the another end, or if we want to send bulk data from one user to the another user. So these are kind of experiments that we conducted, but we can add more experiment here as well. And based on the experiment, we are going to get the results. Now the participants we considered is Alice, Bob, and Eve. So Alice and Bob are generally a communicators, and Eve is the third party. Eve is always a kind of an intruder, right? We are planning to extend this algorithm. So especially I know that lot of students from this lab, they are also kind of working on quantum cryptography especially. So if you are interested, we can probably extend this simulator by including the role of EU, then launch some attacks and see the and then we can show the overall impact while launching a quantum attacks while the data will be transferred from Alice to the Bob. Could be the extension that we are planning to have it for this simulator. Then this is just for a demonstration purpose, we can add the secure channel. So I'll show you that later on. Just wanted to first of all tell you what are the inputs we consider. For performance evaluation, currently we are considering 2 things: security strength in terms of randomness. So we consider NIST test, and then computational speed. That is the key generation, key encapsulation, key decapsulation, those all per time we are considering for that. Now here you can have the message you want to send, how many message you want to send per minute, whether 50, 70, only one message if you want to evaluate how many message, whether your message should be short, medium, long, or custom. So for short, as I mentioned, we consider 50 MB. For medium, I think we hard coded it, but we can definitely make it dynamic as well. And then the custom message also you can write down. So for now, for quick execution, let me consider short, and we're considering Kyber, and the experiment we will consider, let us try one-way bulk to default. And then before we will run this execution, first of all we need to take our participants here. So this is Alice having public and private keys. So when we drag this participant, then it will automatically generate the public and private key based on the Kyber algorithm. Similarly, when we will drag Bob, based on the Kyber algorithm, it will generate the public-private key pair. Please make sure and please consider that currently we are not considering QRNG API, that we are also planning to add here, such that this shared secret key will be changed then, right? Because we are considering to get the API, to get the input from QRNG. But currently it is taking the input from PRNG. So that's the default. This is the default Kyber. It's not a modified Kyber, just to let you know. And then we are going to add a communication channel that the Alice is going to communicate with the Bob. Now we already provided what we want, and we wanted to just execute and check the security strength of this particular communication. So you need to click on run and just wait for a while. I think it should give you results based on the communication that we have provided. Oh. All right. So once it executed, you will have this results. So if you see, this is the summary of the results, where you see that, okay, what is the experiment type, what is the algorithm, what cipher algorithm you use for the classical, what is the message size. So here you can see it's 100 byte, and how many number of runs you did. Okay, so 50, that is what we decided right here. So it will run for 50 times. And then this is the key performance metrics in terms of key generation time, in terms of memory utilization, how much memory it uses, encapsulation, decapsulation, similarly for AES. And then we have also generated a kind of charts, which is for each of the 50 messages, to check the key generation time and algorithm average time. So similarly for memory, for encapsulation, memory decapsulation, these are all chart. Randomness test, I think one of the tests. So please, this universal statistical test, we did something wrong, but this is actually true, just to let you know. We did not actually configure it properly. So we are working on this, but other than that, if you see, this is a Kyber we already tried, and all the tests are, it seems to be pass, right? And this is the p value. So there is another simulator. You can use the different simulator as well, which is provided by NIST, but we integrated that simulator to this. However, I think there is something wrong over here while we are integrating, so we need to fix this bug. But this is a very good simulator, I would suggest, when you want to check the strength of your key. And again, this is the detailed result for each run in terms of execution time, memory, and other things. And this is the data table, similarly, simulation that we have performed. So this is a kind of a simulator we designed. We have a lot of idea to extend the simulator. So if any of you are interested, we would love to. That's it from my side. If you have any question or concern, please feel free to ask. More than happy to answer.
Audience, if you have any question, please feel free to ask. So you can get the like answers from the expert who already worked on real time, so that it would be helpful for you. And moreover, like thank you so much, Darshana, for even you are extending your support for the upcoming researchers to help.
You're very welcome. And I know your students, they are extremely intelligent. I know they're very hardworking. So we would like to have, if they are interested in specifically to extend the simulator or even work with some of the projects related to quantum cryptography or post-quantum cryptography.
Yeah. Questions or doubts, please feel free to ask.
Madam, good evening. If there is any open source tools are available, ma'am?
Yeah, so as I mentioned, for post-quantum cryptography, if you would like to, probably you'll get that library. You can just download it, install it, and then you can use those specifically that for post-quantum cryptography. For quantum, I think generally QisKit people used to have it. I think professor will talk more on that on their session.
Already one of the session they have given a very good like a real time that hands-on they have given. Even they started with the thing they explained well. Yes,
That's nice. I know that
yes,
your students have been working on, especially on quantum cryptography. I don't know quantum cryptography, but quantum technology, and
yeah,
they have using QisKit. Yeah, that's correct.
yeah. So any questions, then we are going to for joining us and sharing your valuable like experience, what you acquired. So this is what like much important for today's faculty development program, because you started with like how the post quantum cryptography works, and then how the hybrid approach, and then how you have implemented, especially like how the Kyber like the algorithm works well, and then the way like you explained is it's like a very good because the flow was it's easy to like understand even the people those who are not much interested in cryptography also. That's what I wondered. Even I too enjoyed a lot. Because and moreover like finally end with because right like only like talking with the theoretical part doesn't looks good, because how we what is the research gap we need to find, and then how to implement, and then simulation, what are the parameters that we need to like analyze, that and all like have to like explain is much important, that you have done well. So thanks a lot for your time and spending time with us. No words to express. Thank you so much.
Thank you so much for this opportunity, and great to have such a wonderful audience, especially and your students. Definitely, thank you so much for this opportunity, Professor. Means a
Thank
lot.
you. Thank you. Thank you so much.
All right.
Thank you. Thank you, CSHO design.
Thank you, sir. Thank you, sir.
Okay.